Hi, everybody. My name is Pedro Sant'Anna. I'm a senior researcher here at Microsoft, and I'm also an assistant professor at Vanderbilt University. So although I have worked quite a bit on difference and difference methods, today in Coachella 2021, I'm not going to be talking about any of my papers, but instead I'm going to talk about Clément and Xavier's paper on two-way fixed effect estimators with heterogeneous treatment effects, which came out at the AR in 2020. And I'm very happy that I'm going to have this opportunity to help Scott a little bit further to disseminate this important paper and help you all understand better what is so nice about this paper. Right, so like broad picture, I think Scott just finished talking about the Bacon decomposition. So I'm going to be very brief about the Bacon decomposition because I think this is going to help us like clarify and stress the added value of Clément and Xavier's paper compared to Andrews Goodman-Bacon paper. Right, so if you think about what Scott just presented and emphasized about the Bacon decomposition, the starting point is I have this two-way fixed effects specification where I have the outcome YIT as my dependent variable. I'm going to regress that against unit-specific fixed effects, time-specific fixed effects, and this treatment dummy, DIT here, that takes value 1 if I am treated and 0 otherwise, right? And in this specification, beta, it is presumably my parameter of interest, right? So what Goodman-Bacon does, like he imposes that additional structure that once I am treated, I am forever treated. So he's going to impose that treatment is irreversible and ask the following question, right? So how does OLS compute this beta hat, right? So beta hat is going to be an estimator of beta, but what kind of comparisons like OLS is actually exploiting to get you the beta hat that you were after? Right, so this is essentially the heart of the Bacon decomposition, right? Is explaining what kind of comparisons OLS is leveraging to compute the beta hat. Right, and now we know, Scott already gave you the detailed explanation that beta hat is going to be a weighted average of several 2x2 DID estimates. And what I want to stress here is that this weighted average is guaranteed to have weights that is strictly positive for everybody in the sample, right? So the Bacon decomposition is going to give to you, right, a bunch of comparisons that OLS is exploiting, and it's going to put all these comparisons in a blender, and each of these comparisons is going to have a positive weight, right? And this is going to be the beta hat. But if you recall, like if you were following this discussion about differences on Twitter, or you're talking to your coworkers or students, right? You have the sense that like, well, suddenly everybody's talking about negative weights, right? Everybody's talking about like two-way fixed effects not being reliable because of some negative weights issues. So where this is coming from, right? So where is negative weights coming from if the weights coming from the Bacon decomposition are all guaranteed to be non-negative, right? So I think this is where I think is important to emphasize the nature of the composition that Andrew Goodman-Bacon it is providing to us, right? And how that like avoids the issue of negative weighting, right? So Bacon decomposition is somehow atheoretical in the sense that it's just explaining to us what kind of comparisons OLS is actually leveraging to compute this beta hat, right? So it's just a way what is going on behind the scenes of comparing which group with other groups, like and how they aggregate together to give you something out of it. But we as economists and social scientists, right, as researchers, very often we don't care about beta hat. We care about the causal effect of a policy, right, on some outcome. And presumably, beta hat is estimating some kind of average of these causal effects, right? So beta hat per se, the type of comparisons per se, that like the OLS is leveraging may not be interesting for us. Like if they're, so what we're really after, it is some causal effects. Right, so then comes the question, well, what happens if we were to impose a set of assumptions, right, causal assumptions from the get-go, such as like parallel trend assumptions or non-anticipation assumptions, like let's impose those from the day zero, right, and say, well, I believe in those assumptions, let's impose it. And instead of trying to decompose what OLS is doing in terms of the compositions of beta half, like two by two DID estimates, let's try a different strategy, right? Let's try to write this decomposition in terms of unit-specific causal effects, right? So here, what I'm going to try to do is, instead of trying to leverage or be explicit about the comparisons that OLS is doing behind the scenes in terms of 2 by 2 DIDs estimates, we're going to say, well, I'm going to impose from day zero, for the get-go, a set of causal assumptions, parallel trends, and non-anticipation. And I want to express the population version of this beta, right, in terms of averages of unit-specific causal effects, right? And this is where you're going to go. So this is where the Chaisemartin and Alto-Follier paper is going to shine, right? Because this is exactly the path that they are following. Like what kind of average causal effect the population OLS it is recovering for this 2A fixed effects parameter, right? So, and even if I impose parallel trends and anticipation, as most difference and difference procedures going to argue that you should do it, right? So what happens in those cases? So this is where we're going to go. This is where we're going to drive. And I hope this is going to help you understand like where this negative weighting, how these complications associated with its effects to make causal inference appears. Right, so let's talk about the Chaisemartin and Alto-Follier decomposition, right, or the French decomposition, if you wish, or this CDH decomposition, if you wish. Right, so first about setup, right? Before we get to the notation, let me stress some things that I think is very important, right? The first one, it is that the setup or the Chaisemartin and Alto-Follier, it is very general in the sense that it allows for treatment to turn on and then turn off, right? I think this is like a nice feature because we're not going to restrict ourselves to setups where treatment is irreversible. So this is the first thing I would like you guys to remember. So even though this is interesting, right, in these slides, I'm going to impose for simplicity that we are in a case where treatment is indeed irreversible. So I'm not going to allow treatment to turn on and turn off, right? Once it's on, it is on forever. And I'm doing this just for simplicity, right? But again, the results of the Clément and Xavier paper will allow for this general on and off scheme. Second thing that I think is important to stress, it is that like this paper by the Chaisemartin and Alto-Follier considers very general sampling scheme, right? So they're going to allow for clustering, they're not going to impose like IID, right? Which also is very attractive. However, in the notation that I'm going to use on my slides, I'm going to restrict my attention to a random sampling scheme, right? Just to make things slightly simpler, right? So their setup, it is more general, and you don't have to tie your hands to this word when I have IID sampling schemes. So this is two remarks that I would like you guys to remember before I go through it. Having said that, let's start digging into the pieces of the CDH decomposition. Right, the first piece, it is the unit-specific treatment effect. Right, so this delta ITG is measuring the average, the individual I treatment effect at time period T from switching treatment for the first time in period G versus never switching treatment on. Right, so it's like I'm comparing what would be the outcome of unit I in time period T if this unit were to first be treated in time period G versus if this unit never receives treatment. right? So this is what I'm going to call the unit-specific treatment effect at time period t. Second, let's denote this error term here, epsilon it. Right, so let's consider this auxiliary regression of the variable, the treatment dummy dit, against a vector of unit-specific fixed effects and this time-specific fixed effects. And this reminder term here is going to be the epsilon it. So once I have this error term, I'm going to aggregate these error terms in a particular weight to define my weights. Right, so my weights here, WIT, going to be get these error terms, WIT, right, and divide them by the average of all epsilon ITs among units, such that they have the treatment on in a given period in time. Right, so what I'm doing, like, get all these epsilon ITs, right, in the numerator, and divide them by the average, right, of these epsilon ITs among units who have DIT equals to 1. So this is going to be my weights. So the first two components of that's going to be important for our decomposition here, this CDH decomposition, it is the unit-specific treatment effect and these weights that come from this auxiliary regression. Next, let's impose this part that we have parallel trends everywhere for in every time period and in every treatment cohort, right? So I'm going to call this the strong unconditional parallel trend because I'm assuming that in the absence of treatment, the evolution of the outcome among units in cohort G, it is the same on average among those in cohort G prime, no matter what is G and G prime. So this is going to assume parallel trends for every unit, for every group of units, for every cohort in every time periods. So I'm going to have, this is going to be the main causal assumption I'm going to impose, that, and also I'm going to rule out that units anticipate treatment. So I'm going to have no anticipation of treatment as well baked into this analysis. Once I have these pieces, like I can go to theorem 1 of the Chaisemartin and Fourier, right? The CDH decomposition. And theorem 1 in their paper states that once under some assumptions like no spillover, no anticipation, and the strong parallel trend assumptions, right, on top of additional structure. So again, this is like in my setup where I have imposed staggered adoption, so irreversible treatment. Under these three assumptions, right, we can answer the following question. So I have this 2A fixed effects population regression, right? And I ask, what is beta? All right, so what kind of causal effect beta here it is actually recovering? Right, and the answer is beta, it is a weighted average of all unit-specific treatment effects. So I'm going to have delta ITG. So again, these are like unit-specific treatment effects. And they have these weights, WIT, right? This WIT is again coming from this auxiliary regression. Right, so what actually beta it is giving to us is recovery. It is a weighted average of unit-specific treatment effects. These weights sum up to 1, right? But surprise, surprise, these weights here can be negative. So these WITs here can be negative. So this is where the negative weighting problem with 2A fixed effects come in, right? So as far as I know, this paper by the Chaisemartin and Fourier, it is among the first ones to highlight that once you run this specification, like beta, like is gonna recover a non-convex aggregate, non-convex average, right, of unit-specific fixed effects, and these weights can be negative. And why negative weights is a problem? right? It's a problem because even in setups where all these delta IT G's, if all of them is positive, it may still be the case that I'm going to get a beta that is negative, which is very counterintuitive, right? So whenever we see negative weight as a possibility, in my mind, this is a red flag. Say, don't go there. Very dangerous, right? And this result of the Chaisemartin and Fourier is giving us exactly that message, right? The second message, so yes, but what happens if you run this specification, right? So here it's telling that some weights can be negative. It's not telling that some weights will be negative, right? So in some situations, it can be the case that all my weights are positive, right? So in general, all weights gonna be positive. From my personal experience, right? And anecdotal, I haven't proven this. In setups where I have like a large group of never treated units, and I have not so much variation in treatment adoption, right? Timing, these weights gonna be positive. Right? This means like, well, I cannot have sign switches in this specification, right? So it can't, if all my weights are positive, what happens is that if my unit-specific treatment effects, they are all positive, beta gonna also be positive. I cannot have sign switch in this word. But does this mean that 2A fixed effects work in this word? Right, so suppose I don't have problems with negative weighting. Does it mean that 2A fixed effects is quote unquote okay? And again, I think this result of Clément and Xavier, it is very deep in that sense, because once you look at this representation of beta, right, from my view, in order for something to quote unquote work, it means that we have to be able to give a good interpretation for these weights, right? So this is the weights here, WIT, should be interpretable in the sense like, I know what kind of aggregation it is going on behind the scenes. If I know the aggregation, right, I know how to interpret beta. But here, these weights like are coming from this auxiliary regression, right? And at least to me, it is very hard to digest or to interpret, to give a proper interpretation for these weights. So even when all these weights are positive, right? Beta here, it is recovering a potentially non-intuitive weighted average of unit-specific treatment effects, right? So even when all weights are positive, right? This result from Clément and Xavier's paper is telling not so fast, Tiger, slow down a little bit, because I'm not sure if you want to follow this route, because these weights are not driven by an economic question. It's not driven like by something that you care about. It is driven mechanically by the estimation method that you're choosing. Me, as a control freak person, don't like that. So I think that weights being non-negative, it is the very minimum requirement, right? But the second requirement is that I have to be able to explain and convince people that these weights are reasonable and easy to understand. If I can't do that, right, I have like some conflicts in my mind, I tend to choose other alternative procedures, right? So the beauty of this result from Clément and Xavier, it is that negative weights, it is a problem, but more than that, the lack of interpretation of these weights, of easy interpretation of these weights is a second problem. So having said that, the question is, well, if you don't like 2A fixed effects, what else can we do, right? So what else is out there that we can do? And here, because I don't have much time to dig into the solution that Clément and Xavier proposed in their paper, but I'm just going to give you a like high-level discussion. Right? So in the paper, what they do, they don't stop at the problems. They go on and propose solutions as well. The solution they propose going to avoid this negative weighting, also going to avoid this lack of interpretation of the weights. right? And furthermore, the solution is suitable to situations where treatment turn on or turn off, right? So they're going to allow for treatment to turn on or turn off. They're going to avoid the problems with negative weights. They're going to avoid the problem of non-interpretable weights, right? But where's the catch? The catch is that in this paper, they're going to focus on instantaneous treatment effects only. So they're only going to look at treatment effects at the time they turn on. Right? So if I turn on and turn off over time, I'm going to zoom in only at the time that I turn on across times. Right? So because I don't have much time to go into the detail and explain the solution that they propose here, I just want to highlight that everything should be easy to implement, right? They have a data package available to implement all this, right? And you don't have to restrict yourself to setups where treatment is on and stay on forever. You can allow situations to treatment turn on and turn off, right? But in this paper, they focus on instantaneous treatment effects. They later on, so Clément and Xavier extend this analysis to dynamic treatment effects as well, but this is like a follow-up paper. I don't have time to dig into that today, right? So to me, main takeaways from this paper. Two-way fixed effects can give you non-intelligible weighted average from treatment effects, right? These weights can be negative, but more importantly, right, they cannot only be negative, they are in general hard to interpret, right? And in this world, what else can you do? You can choose an alternative procedure that does not suffer from these drawbacks, right? So before I turn all this to Scott again, let me walk you through some code that explain these issues, like how to do this in practice, right? And leverage some of the R code. So just 1 second, I'll stop share. I'll share my screen again, because I want to use some of these applications that Scott has been talking through throughout this Coachella course. That's going to help you understand this as well. Right, so in the Baker decomposition, you guys have already seen this paper by Chaisemartin and Orchestra, right, in JHR on the effect of this Castle Doctrine law on homicides and violent crimes. Right, so what I'm going to do, I want to revisit this example and run this CDH decomposition on it to see if we have problems of negative weightings on it. So I'm going to first load a bunch of libraries here just to make everything works for me. The library that is very important in this analysis is the two-way fixed effects, two-way FE weights, because this is the library to run this CDH decomposition, right? Then I'm going to first, once I have loaded all my libraries, I'm going to load the data set that Scott has prepared for us, right? I'm going to call that data set Castle. Next, I'm going to, because in this data set, if units are never treated, they have missing treatment date, right? To use these procedures, I have to replace the missing treatment date by something that is, I'm going to call here infinity. So never treated, it is infinity treatment date. I also going to create this variable DIT, right? So it's going to be treated. It's going to be a dummy variable. If unit I, it is treated in time period T and 0 otherwise, because this is a staggered setup, right? So it's going to be if the calendar year, it is greater than or equal to treatment date. So I do that, create that variable, so we can run the two-way fixed effects regression, right, of log homicide against unit-specific fixed effects, time-specific fixed effects, and this DIT dummy. So I'm going to run this, right, and I'm going to display the summary, right? So I have a point estimate of around 0.07, 0.08. So this means well, on average, this law led to around 80% higher homicide rates among states were actually treated. But we know we have been seeing all these problems with two-way fixed effects, right? So you see this, well, I'm going to do the Bacon decomposition next. So you go do the Bacon decomposition, right? Once you do, you have these three different types of weights, right? And you see here, all the weights are positive, which should always be the case. Again, Bacon decomposition, always going to give you positive weights because that's the nature of his decomposition. But everybody doing differences and differences are talking about problems with negative weights. So once you talk about problems of negative weights, you have to move beyond the Bacon decomposition, right? Which is what we're going to do next. We're going to use the CDH decomposition. And the command is very easy to use, right? So the command is two-way fixed effects. Data set is Causal. The outcome is log homicide. The group here, it is the cross-section indicator SID, right? SID, the state ID. I'm going to have time as year. This DIT is going to be called treated, and I'm just going to run this. So once I run, right, I have here the description of the outcome. So we can clearly see, in this case, following the Chaisemartin and Dalton-Follier, we have 97 different unit-specific ATTs, right? And in this application, I don't have problems of negative weights. So all weights are indeed positive, right? So in this particular application, we don't have any problem of negative weighting. So this means that it is impossible that beta has a different sign as the unit-specific fixed effect, the unit-specific treatment effects, right? So that's the message here. But again, as I said before, negative weights, it is the major problem, right? It's the worst problem ever. But there is also a problem of like lack of interpretation of these weights, which is still can be behind all this analysis, right? So you can also see here, like the fraction of weights that are positive, right? 1 fraction of weights that are negative, 0, which is just going to give you a different set of tools to see if in your application, right, if you have problems with negative weighting or not. So all in all, that's all I have to say for today. I hope you guys find this useful, right? And you find this interesting. And again, Scott, thank you very much for this opportunity. I hope to see all of you guys soon. Take care.